Continue where we left off last time. We talked about how terrible arrays are in Java when you have this nice new shiny thing called lists, or in general dynamic data structures. I remember we are on Piazza and we are on YouTube, so if you have any questions, go ahead and post there. But otherwise, I went through this demonstration where you can create this list and it dynamically increases its size or shrinks depending on whether or not you add elements or remove elements, right? And the remove can be index-based or it could be equality-based, like if you want to remove 32, right? The element 30, the element that is equal to 32 or something like that. And then of course you can use a traditional for loop, but since it is a more sophisticated dynamic data structure, you can use this enhanced for loop. It's essentially a for each loop. For each integer x in my list, simply just print it out. If you don't need access to the index value here, you can go ahead and just use this enhanced for loop, okay? So that is all in the notes. Now what I want to do is I want to look at another dynamic data structure, sets. Sets still hold stuff, but they hold it in a little bit different manner. Sets are unordered. There we go. Collections of unique elements. So what I mean by that is there is no order. There's no first element, second element, third element, last element. They're just elements. It's unordered. Not only that, but they're unique. You can't have 2 5s in a set. That's completely different from a list where you can have as many 5s as you want. Yeah, go ahead.
So in that function for each integer x,
Mm-hmm.
my list, so does that count? Like if there's five threes in the list, so it does that.
It'll go over each. If there's 3, 3, 3, 5, 5, 5, it'll print 3, 3, 3, 5, 5, 5.
Oh, so it prints everything.
Because it's a list. Yes.
Oh, okay.
Yeah. X automatically gets updated on each iteration for you. So instead of saying mylist.get x is equal to mylist.getI, this relieves you of the need of having to do a traditional for loop with an iterator index variable and then getting each element. Right? Sets are unordered though. Right? So let's go ahead and get rid of this code and create, instead of a list of integers, let's create a set of integers. And I'll just call it S for short here. Now, you can't use an array list because an array list is a list. So the usual implementation that I suggest is to use what's called a hash set. Hash is based on hashing, which is a concept that we won't get into, but basically it is a super efficient way of storing stuff using a hash function that you take an object and you map it to an index variable, and then under the hood there is still an array, but it's being used differently. It's called a hash table instead. And this is our hash set. Now, of course, you do also need to import these. Import and import. And it's too small for you to see, but I will go ahead and expand it out up here. All of this stuff is in java.util. So java.util list, java.util array list, hash set, etc., etc. Okay? So we use a set very, very similar to how we used a list. If you want to add stuff, just go s.add, right? 10, 20, 30. And now let's go ahead and print it out and see what it looks like. System.out.println s. Now, is it necessarily going to be in that order, 10, 20, 30? No. Not necessarily. It might be just because it's a small set. But let's go ahead and find out here. 20, 10, 30. It's unordered. When we print it out, it imposes an order. Whatever it just takes the stuff and goes over it in some order. Some order, not the original order that you put stuff in. So how do I get stuff, right? How do I say s.get the ith value, get the first element? There's no such concept there, right? There is no first element. There is no last element. There's no zero indexing. There's no indexing at all because it's unordered. So if I want to iterate over a set and get each element, what do I need to do? I have to use that enhanced for loop. For each integer x in the collection S, or in the set S, system.out.println the element x. Right? Now here this is probably going to end up being the same order, because all it's doing is an enhanced for loop here too. 20, 10, 30. So how do we take stuff out? Well, you can remove by removing the individual elements. So s dot remove 30. Oops. And if I print it out again, I will see that 30 has now been removed from the set, and it's only 10 and 20, or 20 and 10. Right? Let's go ahead and try to add a duplicate. Adding duplicates. Right? So s dot add. 20 and 10 is already in there, so let's try to add 20 several times. A couple times. And try to print it out. Are there going to be 3 20s in there now? Nope, because it's unique elements. All right? It's not going to be an exception, right? It's not going to be an error or anything like that. It's just a no-op, no-noop, or no-op, no operation, right? It's already in there, so I'm not going to put it in there a second time. So those are sets. So if you ever have need of a data structure that holds stuff, you don't care about the ordering, but you do care that it only holds unique elements, then a set is what you're shopping for. Yeah, go ahead.
What would be like a real-world implication of sets? So I'm trying to think of something, and I just want to use a list.
Well, if you want to filter unique elements,
Okay.
take a list and dump it to a set. Right? And now you've got only the unique elements. In fact, we could do that. I'll show you how. Right? So list of integers, numbers, right? Or IDs, right? Is equal to new array list. There we go. And then numbers dot add 10, 20. I'll just add 10 a bunch of times, then 20, then 3 30s here. Let's print it out. There we go. And you will see that there are a whole bunch of duplicates in there. Okay. Now what I'm going to do is I'm going to create a set of integers. Unique elements is equal to new hash set. Now what I could do is I could iterate over each and every single one of these things, or I could iterate over the elements and numbers. I could check, is it already in there, and then not add it, right? That's a lot of work. I'm doing all the work. Why not let the data structure do the work? And just go ahead and blindly add everything. So for integer x in the collection numbers, right? Unique elements dot add x. Now if x is already in there, it'll end up being a no operation, and we'll end up having all unique elements. So let me go ahead and print out unique elements to show that there's only going to be 10, 20, and 30 in there, but of course whatever order it is in there. Not only that, but you don't even need to do that much work. This is called a copy constructor. So numbers. What I'm doing here is I'm creating a brand new set, and I'm giving it a list. And I'm saying, take everything in that list and put it in yourself, right? Put it into the set. And this results in the exact same result. Right? Yeah.
Is there any significance to the fact that even though it's unordered, the set keeps displaying 2010?
No, internally it's the most efficient way, according to whatever hash function they came up with. You'd have to find out what hash function they have. Hash set here. Find. Oh, maybe at the top the hash function is there. No, okay, it's using a hash map, so we'd have to then go to a hash map and find out what's going on. There are too many hoods to look under. It's one of those Russian dolls. You open up one, you got to keep going down there. Yeah.
Does hash set only take a list of numbers?
Nope, it takes anything. So it could take, well, it could take itself. That'll lead to an infinite recursion. It'll take any other dynamic collection, sets, lists. That's all we're going to go over. It'll also take maps in a sense, and we haven't talked about those yet. Right? So a list can take another list, and it's a deep copy. We'll talk about deep copies here in a second. Well, maybe next time. Or you can take a list and make a copy of the list. You can take a set and make a list copy of it. You can any permutation of those four, right? I'll make sure, I'll put this in your notes so that you have it. There we go. Okay. All right, and then finally, the most powerful, my favorite, is maps. All right, so a map is a key value collection. Right? You can store elements according to, you can store elements of any type using a key of any type. Right? So extremely, extremely powerful. It's dynamic. It's a key value data structure where you can map any type of object to any other type of object. So for example, let me go ahead and go back over here to our IDE, and let me create a map. Right? And I'll just call it M for short here. Right? What do we want to map from and what do we want to map to? You can map strings to integers. You can map integers to integers. Oops. Integer to integers. Right? You can map strings to strings. Right? What I'll do here is I will map integers to strings. Right? And I will use a new hash map to do this. Right? There we go. Okay. Of course, I do have to import these just like before. And you'll notice up there that it's java.utils. Okay. So what I can do is I can put things into this map. But remember, I've got two things here now. This parameterization takes two things. That's the key and the value. The key types map to the value types. So what I could do here, and this is just a toy example, I wouldn't do this in practice, but I can put 10 mapping to the string ten. Right? I could put, I could put 20 or 2 and map it to the string 2. Right? And just give me one more thing here. 42. 42. There we go. Now let's print out what this map looks like. System.out.println, and the way that it's going to, the way that it's going to format this is by mapping those keys to each one of those values. So 2, the number 2 maps to TWO, the string TWO. 10 maps to 10, 42 maps to 42. You'll note here that it is also unordered. Right? The keys are not necessarily in any order. The values are not necessarily in any order. Extremely powerful. You can map anything to anything. Think about a regular old boring array. It's kind of like a map, but you are extremely restricted. You can only map keys 0 through n minus 1, and they're all integers. Here I could map whatever I want to whatever I want. I could map strings to strings. I could map a character to the number of times that it appears in a file, right? And then I could have a character counter, right? I could do anything that I want with this map, and it's extremely powerful data structure. You can use it by, say, getting the elements, right? So you can get an element by its key. Right? So if I want to get what 42 maps to, m.get 42, right? And I can store that into a string s. What does 42 map to, by the way? The word 42 hyphenated, right? There it is. I was able to pull it out by using the key. The key opens the door to give you the value. Yeah?
For .get, can you only put the key in?
Correct. Right. And if you replace it at m.put, 42, we'll map that to answer. Right? And then get it again. Actually, I'll just print out the map to show you that it has indeed changed. Right? I've updated the value. I've used the same key, and so now it's clobbered the original value. Right? You can remove things, of course. You can retrieve things. You can do a lot of things with this. How would we iterate over all the elements? So you've got keys and you've got values. And again, it's unordered. This is not necessarily the order that I put them in. Right? In fact, it's not the order that I put them in. You can have an ordered map if you want to. You can also have an ordered set. An ordered set is a list of unique elements, but you can also have an ordered map. I think it's a concurrent hash map instead, or a tree hash map or something like that. I forget what it is. But in any case, let's go ahead and iterate over the elements. And the way that I'm going to show you how to do that is by using all the keys. So the keys in this particular case are integers. For each integer, and I'll call it k, or in fact I'll call it key because I'm not paying by the character here, because that's what it is, it's a key. For each integer key in the map m dot key set. M dot key set gives you a set of all of the keys. You can also do that by values, by the way. Right? You can iterate over the elements. If you don't need the keys and you just want all the values, you can iterate over all the elements by value. Right? We're not finished with that, that original example here, but for the values are strings. For string, str in m dot values. System.out.println str. Now this will simply just get the words 2, 10, and answer because that's what I have at this point, and print those out. 2, 10, answer. This one, I have the key. Once I have the key, I can open the door to get the value. And so I can do something like system.out.println the key plus maps to plus m.get, and then once I've got the key, I just have to get the element associated with that key. And we see that 2 maps to 2, 10 maps to 10, etc., etc. An extremely powerful dynamic collection. Once you start using them and you see the value of them, you will never look back on boring old arrays again. You might never look back on lists or sets either, right? For that matter, because they're so powerful. You can map anything that you want to anything that you want. You could map NUIDs to student objects. You could map reverse. You could map students to their NUIDs. You can map whatever you want to whatever you want. So hopefully you see the value in that. Right? Never go back to old arrays ever again once you've got maps, right? Unless you're using C, right? And then even then, maybe consider bringing in a library of some sort that does support it. Dynamic data structures, that is. Okay. All right. So multi-dimensional arrays. So both languages support multi-dimensional arrays. And what do we mean by dimensional? Well, a regular old array is just one dimension. It's like the number line, or the x-axis. It's one dimension. It's a line. 2 dimensions would be the x-y axis, and you've got 2 space, right? You've got x and y coordinates. 3 space would be x, y, z, and now you're in the real world, right? You can have 4 dimensions, 5 dimensions, 6 dimensions, whatever you want. If you find yourself going up to 3 dimensions, though, rethink what you're doing. 3 dimensions is probably too much, and probably there's a better way of doing what you're doing. But otherwise, 2 dimensions is perfectly fine. 1 dimensions are perfectly fine as well. But sometimes you need 2 dimensions. What do we call those things? Things that have rows and columns of data. 2D arrays? What's another name? A what? A spreadsheet? Okay, was good. What's another name for a spreadsheet? A table, right? Or I heard the mathy term, matrix, right? So 2D arrays have rows and columns, and we call those tables or matrices. 3-dimensional and above, rethink what you're doing. There's probably a better way of doing it. Either by creating an object or creating a structure in C, okay? I'm just going to go ahead and do this in Java first. How do we do regular old 2D arrays here? Int, I'll call it a table, right? You provide 2 dimensions here, 2 square brackets. And you can create a new table, new integer table of, say, I don't know, a 3 by 4. So this is going to be 3 rows, 4 columns, column table. And then once you've created it, you can use two indices. You can use the first index to give you the row, and the second index to give you the column in that row. So how would I set the top leftmost element? Table sub what?
1,
Careful though. Is it 1? It begins at 0. 0 indexing, and it goes and so 0 indexing on the columns as well, and that's equal to 42. What about set the bottom rightmost element? Where is that going to be?
3, 4.
3. Careful. If you're starting at 1, 2, 3, 3 rows, but if you're starting at 0, 0, 1, 2,
2,
and then
3.
3 equals 101. Right? There's no easy way of printing this out, I think. System.out.println table. Let's find out what it does with this. Yeah, it's just going to print out the memory address of this thing. So if you actually want to see what's in the table, you need to design your own for loop to do so. For int I equals 0, I is less than something, I plus plus. Basically what I want to do here is for each row, ... And then what do I do inside? For each column, right? I need another for loop. For int j equals 0, j is less than something, j plus plus. Right? So this is for each column in row I, ... Right? And then you can print it out, system.out.println. I'll go ahead and print table sub I, j. And then I will put a space after it just so that all the numbers aren't, squeezed in on each other. All right. So how do I know how many rows there are in Java? I could hard code it, right? Because I did it up there, 3 and 4. But what if those were not there? Table dot, how do we get the size of a table? Or how do we get the size of an array? Dot length. Right? How do I get the length of the ith column? Or ith row, excuse me. Table sub I gives me the ith row, right? Dot length gives me the length of that row. Or, yeah, here's the row. I know. So number of rows, number of columns in that row. There we go. Right? And let's go ahead and see what this looks like. Of course, it's going to be one big giant thing, 42 all the way down to 101. You'll note here a lot of zeros in between. Why? Java defines a default of 0. It's not very well formatted though, right? Let's go ahead and format it so that it looks like a 3 by 4 table, a 3 by 4 dimensional table. To do that, I'm not going to print the end line. Where should I print the end line? At the end of a row. System.out.print. There we go. And that'll look something like this. 42 at the top left, 101 at the bottom right. If you want to, you can go ahead and format this stuff instead. %4D, right? That will ensure that there are going to be 4 columns for each integer. And then you can also, at the beginning of a row, you can print a nice square bracket, printf, or system.out.printf. There we go. There. And then at the end, you can print that ending square bracket. And now we get something that looks more and more like a table, an actual table here. 42, and down at the bottom right, 101. Zeros everywhere else. Okay. So that's 2D arrays in Java. It's way more complicated in C. Why is it more complicated in C? In C, how do we create an array? Remind me from last week. What? A pointer, and so a pointer points to a memory location, right? How do we create that memory location? We need to malloc it, right? We need to allocate memory, malloc, right? So what I'm going to do is I'm going to go over here, back over to Python tutor, And I'm going to try to adapt this code, okay? What I want is a 3-row, 4-column table. So come over here. There we go. So I want 3 rows, 4 columns. What I'm going to do in C is I need to keep track of those because remember, I don't have the dot length property anymore, right? That dot length is a convenience found in Java. I don't have that here, so I'm going to keep track of the number of rows and the number of tables in 2 variables. Okay? Now, int star array is a regular old array, right? How do I get a 2-dimensional array?
Double star.
2 stars, double star. Right? When you say double star, I kind of hear this, double star. So let's call it int star star. Right? And there's my table. Now, how do I allocate for this table? Let's think of it as a 3 by 4 table. These 3 things are going to, each row is a regular old array of 4 elements, right? So each one of these things needs to be a pointer to this row. This will be a pointer to the second row. This one will be a pointer to the third row. And so that's how I'm going to create it. I'm going to call malloc. And I'm going to, first of all, typecast this so that the right-hand side matches the left-hand side. Now, malloc is going to need to know how many bytes you want. Well, how many pointers do you want? 1, 2, 3, right? So n times. Now, how much memory does each one of these pointers, pointer, take? 4 bytes? That would be an integer, right? So even if it were an integer, would I hard code it to 4? What would I use instead? Size of int, right? But this is not an integer. It is an integer, what am I doing? Pointing, right? So an integer pointer takes that many bytes. Now, each one of these rows is going to have to create a new array of 4 elements. Next iteration, 4 elements, 4 elements. That means I'm going to have to do this in a for loop. For int I equals 0, I is less than n, the number of rows, I plus plus. And by the way, you could go ahead and use num rows, num columns if you really want to. But again, it's an idiomatic for loop. From the context, we know that n is the size of an array. We know that I is an index variable. We don't need to have more complicated variable names than that because it's idiomatic. Right? We don't have to have the idioms explained to us all the time that, well, no, I just meant that it was raining hard when I said it's raining cats and dogs. I don't have to explain myself every single time because it's part of the language. Right? Now, table sub I. I have to initialize the ith row. So I need to call malloc again. And now here, it's going to look something like much similar, more similar, in fact, exactly the same as before. I want a row of m integers. So m times, now each one of these is an integer, and so it takes however many bytes an integer takes. Right? And I make sure to typecast it so that the left-hand side matches the right-hand side. Let's take a look at what this looks. Actually, no. Let's. I'm going to steal the for loops over here, and I'm going to keep. Come on. I'm going to keep a int value is equal to 10. I'll start it out at 10. Cancel that. For each row, instead of printing it out as I would in Java, I will set the values. So for each column in row I, and then I can't use dot length anymore. I have to use n and m. There we go. I'm just going to set the value here. Table sub I j is equal to value, and then I'll increment the value by 10. So it's going to go 10, 20, 30, 40. Next row, 50, 60, 70, 80. Next row, right? Plus equals 10. And I don't need to print it out because we've got this nice visualization, this visual step-through function here, or step-through visualization. There we go. All right. Let's go ahead and zoom out. There we go. All right, so there's N and M, 3 by 4. That's going to be our table. Initially, the table creates an array of pointers because each one of those pointers is going to point to its own row. On the first iteration, that first pointer now points to the first row. The second iteration, we initialize the second row, and that second pointer now points to it. Third iteration, that third pointer now points to the next row. And over here, what we effectively have is a two-dimensional array. We've got 3 rows, 4 columns each on each row. After that point, we can treat it like a regular old 2D array, right? And here's the values. I and j will start out at 0, 0, and so it sets the top leftmost value to 10. Then it continues for each value in that first row. If you wanted to go for each column for each row, you could do that as well by flipping these 2 for loops around, right? Or just simply flipping I and j around, but you have to be careful there because now n and m are not the same. Right? Continuing, right? I then becomes 1, referring to the second row, and 50, 60, 70, 80. And finally, the last row, okay? Now you do have to be careful here. Once you are done, you need to clean up. ... How do I clean something up in C? Remember, you have your own memory management. Over here in Java, who cares? The garbage collector will take care of that for us. Okay? What about over here in C? What do I use? Free. And in this case, it's table, right? Let's find out what this looks like now. Okay? I don't know if can I skip? Okay, ignore everything. There we go. All right, I just wanted to skip ahead all those steps. So here we go. We're done with this for loop here. There we go. And now we're about to free up the table. But what are we actually freeing up? I don't know why there we go. It just didn't visualize there. There we go. What if we free up the table? What are we going to end up doing? What does table point to? It points to this table right here. So what happens when I free it? What happened to those other 3 tables? They're still there, meaning it's a memory leak. Did we talk about Valgrind last time? Yeah. If you run this through Valgrind, it would tell you that you have 3 by 4, 12 times 4. 12 times 4 is going to be 48 bytes lost. Right? Why? Because you clean up these pointers, but now you don't have these 3 pointers pointing to this memory and this memory and this memory. And you've effectively lost access to that memory. Do we want to see Valgrind again? Otherwise, you'll see it tomorrow in your lab. You want to see it or not? Yes? Okay. Edit the code. I'll prove it to you. There we go. And save it. There we go. Uh-oh. Okay. I will relaunch the IDE. I lost the connection. There we go. All right, so this is, I just cut and pasted there. This is honors GCC demo. Oops, .c. All right, there we go. Run it. And of course, it doesn't do anything because we're not actually printing anything. But let me go ahead and run it through Valgrind. Just as I predicted. Exactly 48 bytes were definitely lost because of a memory leak here. Remember, Valgrind is a dynamic analysis tool. After you've compiled, after you've got a working program, it can simulate the run of the program and monitor everything that goes on with the program. So it can find problems like this at runtime. That's why we call it a dynamic analysis tool. Static analysis tools are like linters, like using the wall flag in a GCC. And that does it before the compilation process. Valgrind can be used to determine a lot of other things too. And there are other dynamic analysis tools like profilers. You can run a profiler to find out where is my program seems really, really inefficient. Where am I spending most of my time? You're spending most of your time over in that function over there. Okay, I'm going to focus on that function and try to optimize it. Right? Various tools like this exist. But exactly 48 bytes have been lost. So let's come back here and fix this. I can't just clean up that table. What do I have to do first? Clean up each one of those rows. So in other words, I need another for loop to do it. Right? I will clean up each row. For each row, clean it up. Free it. Dot, dot, dot. Free the ith row in the table. And then you can free the table at the end. And again, let's go ahead and visualize this execution. Yeah, go ahead. While we're waiting. Say what?
Doesn't matter the order which you create them.
You can go backwards and forwards. Doesn't matter. As long as you don't lose pointers before you clean them up. Yeah.
So the table is the array of an array.
It's an array of an array. It's an array of pointers.
Uh-huh.
Each one of those pointers points to an array. Therefore, it's an array of an array. Right?
That's why it's a table.
Yeah.
So when we claim the table, I would
Yep. So here, let's go back here. All right. So there's all my pointers here, and now we'll start simulating this this run here. So we free up. Come on. We free up that first table, and you see over here it's a little jokey way of visualizing that is by turning it into the poop emoji here. But these two things are still pointing to those other two rows. So we clean up the second row, and we clean up the third row, and at that point, those arrays are now cleaned up. Those pointers still need to be cleaned up though. So we clean up by freeing up that entire array. And when I do that, let me run it through Valgrind one more time to show that it has now been fixed. Clean up those first. GCC, Valgrind, and now 0 bytes will be lost. Right? It's not even reporting it because nothing was lost. In fact, no errors, from 0 context, so no errors at all, right, that it could detect. Dynamic analysis tools are not a cure-all. You can still have bugs that are left undetected by Valgrind. But Valgrind can detect things like, say, something that Bret Hart would admonish you for, right? Int a is equal to null, right? And then I could say that a is equal to 42. What am I doing there? I'm not checking for a null pointer. I'm actually dereferencing a null pointer and trying to put 42 into it. Right? Let's see what Valgrind has to say about that. Error. Right? Let's see. Where? There was definitely an error, segmentation fault. Tell me where, though. It's not able to, because it told me that it happens at a memory address. I can fix this. Let me recompile it with this nice special flag here that we'll be eventually talking about here very soon. G. G is short for the GNU debugger. Right? What that does is it retains all of the line numbers, and it retains all of the function names and variable names and all that stuff that normally gets thrown out the window when it gets compiled to machine code. And now when I run this through Valgrind, it'll actually tell me the line numbers that all this stuff happened on, right? It should. Oh, darn it. I have to give it more information probably. Oh, no, there we go. There. Line 10 and line 12, right? Nope, those aren't the lines I want. Okay. Rerun. Come on. I have to give it special commands, I guess. Not stack, malloc, or free. Why are you you're giving me a seg fault, but you're not detecting it? Come on. You should be able to detect this. There we go. Process terminating with the segmentation fault. Access not within a match region. There we go. Line 24. What happened on line 24? I dereferenced a null pointer. So if you believe this happened as a result of a stack overflow in your program's main thread, unlikely but possible, you can try to increase the size of the main stack, blah, 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 blah. Okay, so this definitely didn't happen because of the stack overflow here. This is a tool that you'll get more use out of in this week's lab. You'll have to fix a memory leak just like we fixed this one. Okay. I'll make sure that you have this in the notes as well for the C version. And there we go. There. Okay. All right. What else? Don't remember. Do we have anything else? Bookkeeping, dynamic arrays, 2D arrays. All right, then let's talk about shallow versus deep copies. All right. So there are two types of copies. If you want to make a copy of an array or a 2D array or whatever, a shallow copy of an array is simply when two references, say pointers in C or variables in Java, refer to the same thing. Okay? A deep copy, and I'll emphasize that as well, is when two references refer to completely different areas of memory with the same contents. Okay? Now what I'm going to do is I'm going to come over here to C and demonstrate that in, say, this visualizer. Okay? Int star A. In fact, I'm just going to copy this because I don't want to deal with it. I don't want to retype all this. So let's walk through this really quick though. So I'm going to create an array of size 5 of integers, and I'm going to set them equal to 10, 20, 30, 40, 50. Okay? And then I'm going to create another reference, int b, and I'm going to set it equal to a. Okay? Now, I can make changes to a, I can make changes to b. Let's go ahead and make changes to b. Let's set the first element equal to 42. Actually, let's make that change with respect to a. Now let's go ahead and print out b sub 0 is equal to %d, and the line b sub 0. Predict what it's going to print out here. Is it going to print out 42, or is it going to, remember the original was 10, 20, 30, 40. Oh, 10, 20, 30, 40, 50. Right? So the first one is going to be 10. Is it going to print out 10, or is it going to print out 42? I changed A, right? But did I change B? Okay. Let's find out. Let's visualize this. Oh, come on. What are you complaining about? Oh. Duh. There we go. Int star, not star int. Right. Close that. All right. So I'm creating A, and I put in 10, 20, 30, 40, 50. Now on this next line here, what is B going to end up referring to? The same thing, right? Nothing on line 8. But after line 9, what's it referring to now? The same array. This is what's known as a shallow copy. I've got two references, pointers in this case, pointing to the same array. So when I change A on line 11, what's going to happen? That 10 is going to transform into a 42. So when I print out B sub 0, what is B referring to here? It's referring to the same array, which has 42 as its first element. Right? And it prints 42 up here. This is known as a shallow copy because you've got two things referring to the same thing. So changes to one affect the other. What if you don't want that? What if you want a deep copy? I want two completely different arrays. I just want them all to have 10, 20, 30, 40, 50. I want to copy that over so that if I make changes to it or if I make changes to the original, one does not affect the other. Okay? So let's go ahead and edit this code. This is such a common operation that maybe we should just put this into a function. And that's actually the next topic, how to use these with functions. So I want to create a new function. This function creates a deep copy of the given array. of integers. Okay? So what should I call this thing? Deep copy? Okay. And it's also integers, so I'm going to append int, because you might want a deep copy of doubles, you might want a deep copy of chars, whatever, right? All right. So what should I take as input here in C? Obviously, I need an integer array. Does that look like an integer array to you? That looks like one integer to me. You need the star. Now, be careful here. You were doing this all last week in your hack 6. When you have an int star, like an RGB value, or a int double star, a CMYK value, that was referring to one thing, right? A pointer is just a memory location. A pointer can point to one thing, or it can point to the beginning of many things. Right? And that's actually how memory works. Let me pull up this new figure. I don't remember if I showed you this figure or not, but I'll show it to you again. This is how memory actually works in most programming languages with respect to arrays. And it's why we use zero indexing. An array is simply just a memory address. It starts at some memory location. Then the first element is 0 bytes away from that memory location. So we end up having array of 0 is going to be array, a memory location, plus a number of bytes away from it. And that's going to be 0 times however many bytes an integer takes, which is 4. So that ends up being 0. And we end up pointing to the beginning of the array and the first element in that array. Now, what about if you want the second element? Well, that's going to be at that location, but then 4 bytes away from it is the next element. And so we have 1 times however many bytes an integer takes, in this case 4, giving me the, come on, you're not going to highlight that? Okay, fine. You're giving me the second one. Third one, fourth one, fifth one. That's why we use zero indexing, because an index is nothing more than a memory offset. Just go as many bytes as you need to over. If there are, if you want the third element, that's going to be wherever the start of the array is plus 8 bytes over, and it can jump to that memory location by using this syntax right here. Right? You can also, by the way, manually use this syntax if you really want to, but there's no cause to when you've got this nice syntax over here. Right? And it also doesn't work in Java. Right? Okay, so how do we tell it that that's not one thing? That pointer is not pointing to one thing. That pointer is pointing to many things, 5 things. What else do we need to tell the function? The size. Right? You could call this size of array if you want to, but again, idiomatic variable names here. If I gave you an integer pointer and n, implicitly n is telling you how many things are in that array. Okay? What am I going to return here? Just one integer? A whole array, right? Because you're going to give me the array 1, 2, 3, 10, 20, 30, 40, 50, and I'm going to give you a new copy of that, a deep copy of that. So how do I give you an array? That 10, 20, 30, 40, 50, that's over there. You can access it over there. It'll be a pointer. Right? Now, how do I go about actually writing this function? I still, of course, need an integer pointer for the result, or in this case, I'll just call it copy, or C for short. Right? And I will, of course, need to create a new integer array using malloc. Right? Because could I do something like this? Int n. Syntactically, I could get away with this. What's going to happen, though? Do we remember what kind of array that is from last week? Let me jump all the way up here. That is a static array. Static arrays are allocated on the stack. When I return from this function, what happens to that stack frame with my 5 integers in it? Goes away. I don't want it to go away. So I'm going to have to use the heap and call malloc. Right? N times size of int. Right? Because if you gave me something with n elements, I'm going to create a new array with n elements, or n places to put those elements, and then I'm going to copy each one of those over. For int I equals 0, I is less than n, I plus plus, another idiomatic for loop here. The copy of I is equal to the original array. and return C. I'm not doing any error checking here, but of course you could if you wanted to. If you gave me an invalid pointer like null, I could return null. If you gave me an invalid size like negative values, or you can't have an array of size negative 10, can you? No. So I would return null in that case. Okay. This is a deep copy. So let's take a look at that in action. Instead of this, let's go ahead and go with deep copy of A and N. Undo. I still want to change it though. There we go. So deep copy, I will change A. Now what's your expectation on B? If there are two references pointing to two different things, and I change one of them, would you expect this one to change?
No.
Nope. So let's visualize this execution. What? Right. Oh, int. Close. We indeed live in a privileged society when we have to wait for a web browser visualization for up to 10 seconds and then we get impatient, right? It must be now. That's pretty damn amazing, right? Anyway, 10, 20, 30, 40, 50, we call deep copy. Inside deep copy, we create a brand new array that is completely separate and distinct from the original array. We copy over all those values so that when we return to the function, we've got now two arrays. So when I make changes to A, great. Those changes are not reflected in B. And it ends up printing 10, as you can see up here. So I'll make sure that you have this in the notes. But otherwise, oops, jump all the way down. There we go. All right. There we go. All right. But otherwise, that's how you do it in C. What about Java? We'll go ahead and blow this away and translate this. Let's translate this part right here. Well, do I need to keep track of the size of the array in Java? Nope. Do I have pointers in Java? Nope. I have references though. And do I have malloc in Java? Nope. How do I create a new array of size 5? New int 5. Right. And then not n, but a.length. And otherwise, it's all the same. There we go. Now let me show you deep versus shallow copy here. Int b is equal to a. And I will make the same changes I did before. What was the change? I made a equal to 42, and then I printed out b. And the only change I'm going to have to make here is system.out.printf. Format that. Nice. What's it going to print? Remember, this is a shallow copy. So 42. How do I make it so that it's a deep copy? I could come back over here, paste this code, and adapt it. Or I could think to read RTM, read the documentation, read the manual. How do I make a deep copy? Arrays dot deep. Oh, no, it's not called deep. It's called copy. Copy of. There we go. Copy of the original array, A, and I will make B point to it. So what the heck is this other parameter right here? I don't know if you can read it, see it, but here, 0. Let me go ahead and put 0 so that it actually compiles so I can jump to it. You can read that. There we go. You can read that documentation. That's easy. There we go. Copies the specified array, truncating or padding with zeros if necessary, so that the copy has a specified length. That's the other one. That's the new length. So if you want to copy over 10, 20, 30, 40, 50, you say, I want to copy all 5 of those elements. For all indices that are valid in both the original array and the copy, The two arrays will contain identical values. So 10, 20, 30, 40, 50. For any indices that are valid in the copy but not the original, the copy will contain 0. So in other words, if you copy over 10, 20, 30, 40, 50, but you give it, I want that new length to be 10, it'll be 10, 20, 30, 40, 50, 0, 0, 0, 0, 0, 5 zeros. Such indices will exist if and only if the specified length is greater than the original array. So by implication, if I said I only want 3, that means that you're only copying the first 3, 10, 20, 30. Let's see that in action. Right? Copy of, if I say 5, or array a.length, the copy of the original array, let's go ahead and print that out. System.out, system.out.print. I will print ln, let's say, b. And you can see here that it's going to be a copy of 10, 20, 30, 40, 50. Unfortunately, it won't print out nicely, so there is also a solution for that, though. Now that I'm not dealing with only single arrays, arrays dot toString of b will conveniently print it out in a nice format. 42, 20, 30, 40, and 50. Remember, that's because I changed it before I copied it. So let's go ahead and get rid of this stuff for a second and see that the original is indeed, oops. I do need this. There we go. Because it's the declaration, 10, 20, 30, 40, 50. If my length here is plus 3, what will this end up printing? 10, 20, 30, 40, 50, 0, 0, 0. 3 extra zeros at the end. If I said minus 3, in other words, 5 minus 3, I only want the first 2 elements. What will that end up printing? 10 and 20. But those are indeed deep copies. If you make changes to it, say b of 0, or let's go a sub 0 is equal to 42 now that we've got our own deep copy, I will go ahead and print out a and b. So if I set the first one to 42 on a, but I don't change b, you can see that it's reflected in a, but not in b. 42, 10 is still left there. No need to write your own, no need to roll your own. You could just use copy of. There is a copy of version for every single type, including objects and including strings, etc., etc. Yeah? Oh, all it does is it takes this array and formats it with square brackets and commas. And so it converts this array to a string so that it can be printed. Yeah, before it was just printing a memory address because arrays do not have methods in them. Yeah?
So are arrays in Java also kind of like pointers? Because they didn't
Arrays in Java are essentially pointers. In fact, that's what it was. Let's go ahead and, oops, nope. Why? Undo. Come on. All right, fine. A and B. Let's just go ahead and print out A here. That gobbledygook right there, oh, come on, is equal to 42. There we go. That gobbledygook garbage right there, that's a Java virtual machine memory address. And it will be the same each time I run this because it's virtual memory. So it's deterministic and it will load it up in exactly the same spot every single time, I believe. 1DBD, 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 16A6, right? So it's going to be deterministic and it's going to load it up in the same memory location every single time because it's the Java virtual machine's memory location. Oops. That's not human readable. It's just a memory address, a virtual machine memory address. And so it's not too useful. So what this does is it basically does what we did, but you don't have to write your own function to do it. All it did was goes through each element, appends it to this string, adds a comma, space, comma, space, comma, space to it, and then not the last one, of course, and then puts square brackets around it, and then gives you a string representation of it. Right? So this is a deep copy. And there's no need to roll your own. Excellent. And again, oops, I'll put this into the notes for you. Java. All right. deep copies. By the way, there's an easier way of doing it in C. You don't have to roll your own here either, but I don't want to get into it. Instead, it's memcopy. So memcpy is short for memory copy, and you can read all about that. It's in the string library for some reason, but otherwise there's the destination. It has to be big enough to hold what you're going to be copying, yeah, copy of memory. Yeah, I believe so. And then there's the source that you're copying. So if you just have one big chunk of memory, it will copy this chunk over to that chunk, and you have to tell it how big of a chunk it is. And so it will copy it all with one command without having to write your own function to do so. And it's generic. It will these are generic void pointers. It will take an array of integers. It will take an array of doubles. It doesn't care, because all you're doing is saying, I want to copy n bytes. And that could be 1,000 bytes. It could be 1,000,000 bytes. Copy that 1,000,000 bytes over to that 1,000,000 bytes. And it gets it done with one. An example, maybe? Here. I've already set up the memory, so all I need to do is go memcpy, copy into the copy array, and be done with it. Yeah, go ahead.
Would this stuff work as well with like files?
No, because it's only memory, and memory I mean, technically the file system is memory, but you have to dump it to the file system, because files in the sense of programming means that it's been loaded up into memory, not persisted out to disk. Right? But you can make system calls to say, copy that disk place to another disk place, I think. But those would be some arcane system calls. Right? So let's see this visualization. I wonder what it's going to do. Because this said that it was in the string library, and I have not included the string library, but apparently it does for you. Great. Next, 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 next. 10, 20, 30, 40, 50. Next. There, deep copy. So, okay, fine. C is a new one. And mem copy. All in one shot. We didn't have to do a loop at all. Right? I don't need you at all anymore, for loops. But no, you can use it if you want. Right. Right, questions so far? No? Okay. You guys don't have that many questions at all. And I was surprised, and hopefully the grades will reflect that I'm pleasantly surprised that there's only like one question on Hack 6 at all. So bravo to everyone. Yeah?
That was because like everybody went to the SRC thing, and it was like,
Oh.
Yeah, no, I had a lot of questions there.
Oh, okay. All right. I don't see these things, but as long as they're getting answered somehow. Great. One last thing. Let's go ahead and just use this example. All right. So I copy everything over, and then should I be making changes to it? C sub 0 is equal to 42. So you're the deep copy integer function right now. I gave you an array, and I told you how big it was. I asked you to make a deep copy of this thing. I want 10, 20, 30, 40, 50. You make it 10, 20, 30, 40, 50, but then for some inexplicable reason, you went ahead and changed the first one to 42, just randomly. Does that sound like something I asked you to do? No. So, it's perfectly valid though. In fact, I'll just take this over to, not all the code. I'll just take over this part of the code, put it over here, and then I will take my function and put it over here. There we go. And gcc demo.c. All right, you're going to complain about the string library. Fine. Don't ask me why it's in the string library, but that's what we're getting to next. There we go. Run it, and we see that it's 42, right? Because it's been changed down here, right? So I was able to do that because I gave you an array. In fact, we can also change the original, by the way. ARR, we'll just screw everything up, right? Screw up both the original, screw up the copy as well, right? Should we be allowed to do this? No. So I can make a promise, right? And it is actually I'm crossing my fingers and putting them behind my back because it's only an initial promise here that I'm not going to make changes to it by making it const, right? Now, this is going to be const. When I try to make change, I'll just get rid of this and just focus on this here. I'm making a promise that I am not going to change the original array, right? By saying that it's constant. Const, short for constant, right? I'm not changing it. I'm not changing it inside this function. Of course, over here we can change it all we want because it belongs to us, right? It's not a constant array. You can make it a constant array if you really want to. What's the point though? You can never change it. So once you've created a chunk of memory, that garbage that was there, you can never change that garbage. So don't do that, right? So anyway, I've made this promise here. Now what the compiler is going to say is you can't do that. You promised that you would not make changes to array, but you did in fact do so on line 8. So error, you can't assign to a read-only location. So getting rid of this and compiling again, I'm keeping my promise. Now I said that it was a pinky swear and that you can still violate that promise indirectly. You can go ahead and go with, I don't know, int star b is equal to ARR. Then you can go b sub 0 is equal to 42. Now, I snuck it by the compiler. Compilers are not very smart, right? If they saw that ARR sub 0 is equal to 42, that's a direct violation of your promise right there. But it's not going to get smart enough to figure out that this is a shallow copy. You can go ahead and make changes to that shallow copy affecting the original without violating your promise. Right? This is me, crossing my fingers here. Save this and show you that in fact the compiler will not complain about this. It'll complain in that it's a warning. Wait a second, you made a shallow copy. I don't know about this. You could be making changes later on. You could be violating your promise, but I don't know. Right? You're on your honor, right, to not do that. But in fact, I did, right here on line 9. So it is only an initial promise, right? Getting rid of this gets rid of the warning and, of course, the error. Right? And it's unchanged. Okay? B is the copy. So using the const keyword over here will ensure that nobody can make changes to it. Unfortunately, in Java, there is no const keyword. There is a final keyword, but it doesn't work. It doesn't work like this does. Right? There is no way to prevent somebody from making changes to your array if you give it to a function. It can make changes whatever it wants to. Right? There's no way to prevent that. Yeah?
So there's no way to prevent that in both C and Java?
Well, there's no way to 100% guarantee prevent it. I could always make a shallow copy and then, you said the compiler is saying stop, don't go around me, and then you just step around the compiler, right? That's why it's just a little bit of a promise. Right? Of course, it's a design thing, right? You're advertising to the world, I'm not going to make changes to it, right? You can have a high assurance that I'm not going to do it because the compiler wouldn't let you, right? But of course, I could go around behind your back and stab you in the back and say, I am making changes to your array or whatever, right? There are always ways to do that. Right? And in Java, unfortunately, there's no way to even make that promise. You might have seen things like, say, the final keyword. That doesn't do anything. Did it change anything? I'm making changes all I want down here. Right? I'm making changes to the array. It just means that I can't do something like this. A is equal to a brand new integer array of size 10. That will be a compiler error. Right? Once I make A point to this memory location with 5 things, I can never make it refer to something else. It doesn't say anything about me changing the contents of that array. You could change it to 42, 42, 42, 42, 0. You can do whatever you want with it. You just can't reassign the value. That's what the final keyword means. And we used that before with, let's say, pi, right? Final double pi is equal to 3.14. Trying to change pi to be 4, that would end up being a compiler error. Okay. More on functions and using arrays and functions, giving arrays to functions, returning arrays from functions, however much you want to see next time. All right. So no questions? Okay. Then I'll